Welcome to the Explainer. Let's just jump right in today because we're taking a journey deep beneath the surface to look at some of the most powerful, honestly kind of terrifying forces on our planet, the ocean's absolutely loudest sounds.
Real quick before we dive into the deep end, I want to mention how we put this specific explainer together. We actually used some modern AI research tools, including Notebook LM, to help analyze and structure the massive amount of information here. But don't worry, every single piece of content was meticulously reviewed, edited, and adapted by me to make sure it is 100% original and scientifically accurate. It's just a really rigorous, forward-thinking way we're handling research these days to bring you the best stuff.
Okay, Section 1, Nature's Loudest Extremes, from volcanic blasts to whale clicks. So to really wrap our heads around the sheer scale of oceanic sounds, we've got to look at nature's absolute loudest extremes. We're talking about acoustic events that totally defy how we normally think about volume. Take the number 4,800. That is the staggering distance in kilometers that the 1883 Krakatoa volcanic eruption was heard. I mean, to put that in perspective, that's literally like standing in New York and perfectly hearing an explosion going off in San Francisco. No way, right? The sound wave from Krakatoa was so unbelievably powerful, it traveled around the entire planet 4 separate times. It was so violent, it actually ruptured the eardrums of sailors who were 65 kilometers away from the blast. Just wild. And hey, the biological world? It has its own crazy extremes. 230 decibels. That right there is the volume of a sperm whale's click underwater. It is the single loudest sound made by any animal on Earth, period. It's so intense, researchers actually think a close-range burst from a sperm whale could theoretically stun or even kill its smaller prey. If you were a human diver swimming just a few meters away, it would completely disorient you. Moving on to Section 2, the Tonga Megasound, a submarine explosion for the history books. Fast forward to January 15th, 2022, when a brand new acoustic titan woke up. The Hungatonga Hunga Ha'apai event was, well, there's no other word for it. It was apocalyptic. It was the largest submarine volcanic eruption we've seen in nearly 150 years. We're talking cumulative magnitude 6.5 seismic disturbances in the solid Earth, a devastating mega tsunami ripping across the Pacific, and atmospheric gravity waves that literally circled the globe multiple times. It released this immense, almost incalculable amount of energy across every single domain, the atmosphere, the solid Earth, and right through the water column. Now, to actually hear an event like this underwater, scientists look for something called T-waves. Basically, these are hydroacoustic tertiary pressure waves. They move horizontally through the ocean at the speed of sound in water. For the researchers, these T-waves are absolutely crucial. They're the acoustic evidence, leaving this telltale sonic signature of the eruption as it travels through the deep sea. Which brings us to Section 3, listening with ocean robots, capturing the deep sea data. So, how do you actually listen to a sound wave that's echoing across the dark, vast expanse of the Pacific Ocean? Well, researchers relied on 2 totally different types of underwater microphones, or hydrophones. First up, they used 24 mermaids. These are so cool. They're these freely drifting robotic floats that autonomously park themselves deep down between 500 and 1,500 meters in the water. Then, they supplemented those mobile robots with data from the IMS, the International Monitoring System. The IMS uses 11 moored, tethered hydrophone triads, meaning they stay locked in fixed positions. And this brilliantly illustrates the immense scale of that network. See the red triangle? That's our volcano. And all those lines radiating outward? Those are the Great Circle paths stretching out to the dozens of drifting robots and tethered sensors spread thousands of kilometers across the Pacific Basin. It's a completely unprecedented hydroacoustic array. But here's where things get really interesting. When scientists actually looked at the acoustic data coming in, they hit a massive roadblock. Why on earth did sound levels vary so much between sensors that were similar distances away? Think about it. If you have 2 robots sitting exactly 3,000 kilometers from a volcano, you'd logically expect them to hear a blast at roughly the same volume, right? But they didn't. The data was a mess. Some sensors picked up a massive booming signal, while others barely registered a whisper. It completely defied basic logic about how sound is supposed to spread. Section 4, the underwater obstacle course, acoustic speed bumps on the seafloor. To solve this mystery, the researchers realized they had to completely rethink the physical structure of the ocean itself. You see, the ocean isn't just a giant, empty swimming pool. Take a look at this cross-section. That jagged line at the top, that's the seafloor. Notice how those underwater mountains physically poke downward into the space where the sound is trying to travel? Scientists look at this specific 3D area around the direct sound path, something they call the first Fresnel zone, which you can also see mapped out below. This zone basically acts like a massive underwater obstacle course for RT waves. The sound is quite literally crashing into mountains. And this physical interference brings us to a huge concept from this study: bathymetric occlusion. In plain English, it's an assessment of the number of seafloor obstacles in a T-wave's path. Think of it as a strict measure of path blockage. Just like hills or tall buildings will block your cell signal on land, these massive underwater mountains physically dampen, scatter, and severely distort the sound energy as it tries to make its way across the Pacific. So, to prove this was the culprit behind their messy data, the scientists created a seriously clever algorithm to calculate an occlusion count, basically a score for how blocked a specific path was. Here is how they did it, step by step. First, they focused their mathematical model exactly at a depth of 1,350 meters, because that is where the T-wave energy is at its absolute strongest. Second, they mapped out that first Fresnel zone, that oval of influence we talked about, along the direct sound path. And finally, step 3, they literally counted the exact number of seafloor obstacles intruding into that specific zone. All right, the final piece of the puzzle, section 5, cracking the acoustic code, the eureka moment in the data. Okay, so picture this. They have their high-tech robotic sensors, recordings of the loudest submarine blast in a century, and a mathematical count of the underwater mountains blocking the sound. When they finally threw all this data together, the math worked flawlessly. It yielded this highly specific, beautiful number, 5.6. Their new model predicted a 5.6 decibel reduction in sound pressure level for every logarithm of occlusion count. Put simply, they finally discovered the exact mathematical rate at which the rugged seafloor was eating up the volcano's acoustic energy. The crucial takeaway here is that this single bathymetric occlusion model explains a massive 88% of the T-wave sound pressure variance across the entire ocean array. Guys, for observational Earth science, that is a phenomenal, wildly successful result. It completely cleared up all that confusing data. Those sensors that were mysteriously quiet earlier, they weren't malfunctioning at all. They just had a heavily blocked, highly occluded path to the volcano. Now, you might be asking, why does this matter to us? Well, as the study points out, understanding this ocean-scale variability aids in figuring out exactly what caused the sound, how big it was, and where we should put our sensors next. By knowing exactly how to correct for all that seafloor roughness, scientists can now take pretty much any hydrophone recording and accurately calculate the true explosive power of submarine volcanoes or underwater earthquakes. Plus, it tells them exactly where to strategically park their ocean robots in the future so they have a clear, unblocked line of hearing across the whole ocean. Which leaves us with a final, pretty provocative thought. How might these high-tech models and those freely drifting ocean robots help us monitor hidden explosive phenomena across our vast, largely unmapped oceans in the future? As we deploy more of these autonomous mermaid floats and arm them with algorithms that perfectly decode the bumpy seafloor, the deep ocean is going to slowly give up its most explosive secrets. The loudest sounds on Earth, well, they won't be able to hide from us anymore. Thanks so much for joining me for this explainer, and keep your ears to the ground, or, to the water.